Okay, so the first speaker of this session and the penultimate speaker of the entire conference is Arkady Tseytlin, who's going to tell us about semi-classical quantization of superstrings in AdS 5 times S5.
So I should start with saying that I returned my key, but my room was G5, and that's why I'm talking about Green-Schwarz string. So what I want to do is to give some broad perspective on some recent developments, which were largely motivated by progress in understanding Green-Schwarz string in AdS 5S5 through recent years. And in particular, this plane wave recent anxiety was motivated also by understanding string theory, essentially one loop correction in this theory. So this string theory in AdS 5S5, even classical string theory, by classical I mean n infinity, contains lots of interesting information, contains information about functions which enter various observables like the entropy, say Wilson loop of two parallel lines, anti-parallel lines, or anomalous dimensions. And that's what I'm going to concentrate on. So what we can certainly do is compute these anomalous dimensions, strong coupling at large lambda. That means in alpha prime in string theory. And for that exercise, which turns out to be very useful, as was demonstrated by recent progress by BMN in particular, I would like to stress that actually looking at Green-Schwarz action is useful anyway, not only in particular with BMN, but in more general context, and largely motivated by suggestion by or understanding of Gapser, Klebanov, and Polikov. I should stress that in open string sector, namely computing expectation values of Wilson loop, essentially expansion of based on Green-Schwarz action was done earlier. So it's not something which is completely novel idea just to try to start with Green-Schwarz action and expand near some classical string background. But in the closed string sector, that actually leads to much more interesting information about AdS CFT. So let me start with some general remarks about Green-Schwarz action. And essentially, it contains bosonic part and fermionic part. And fermionic part has very simple structure. Essentially, covariant derivative containing, projected to the world volume containing usual connection part, and a part coming from self-dual 5 form. So on AdS 5S5 background, this term essentially produces certain mass term in this fermionic action. So it's a very generic phenomenon. If we have, say, some string excitations near some long string, or actually some string background, by background I mean classical string solution, we get quadratic action to leading node in alpha prime, which will be massive fermions. So more generally, the whole Green-Schwarz action in AdS 5S5 can be put in several simple forms. In particular, there is a very simple gauge in which it looks two lines, but unfortunately, it's in covariant gauge, as it's well known, it's degenerate for small strings. A better way to look at Green-Schwarz action is actually to use light cone gauge, and that is possible and in fact quite systematic approach, which basically very similar to a flat space case, which leads to essential, when a shortcut, a quick way to understand how to fix a light cone gauge in this case is to think of Pointlike coordinate parameterization of AdS and fix diagonal gauge for the metric. But one can also use more systematic phase space approach, but essentially the action looks very simple. It's a quantum, if we expand in sigma, it's a quantum mechanics with canonical kinetic terms for bosons and fermions, and then there is quite complicated Z-dependent, so radial AdS-dependent terms, but certainly using various methods to deal with such action exactly would be very, very interesting. It's only quartic in fermions, so it's not really that complicated in fermionic part, but it's certainly very nonlinear in bosonic part. So what I'll be discussing is mostly expansion of this action to order by order in alpha prime when this nonlinearity will be sort of resolved. There are various issues related to that action, like we can think of what kind of limits we can take, lambda to 0, etc. It's not the current subject. I just trust that this action seems to be a very nice starting point for various attempts to understand the string theory better. So the question we may try to address, and actually the basic question, is what is the string spectrum AdS5S5? And the recent progress was is based on suggestion to look at certain sexes of states which carry large quantum numbers. And then what we can do is just do alpha prime expansion near a particular string configuration. So we can be motivated by flat space examples. Think of string, point-like string moving along, say, x9 direction, and do alpha prime expansion in flat space near such string. This is exactly equivalent to light cone gauge quantization for Green-Schwarz action. One loop correction will just give you the spectrum of small string excitations, which in the sector with momentum p. So instead we can look at fluctuations near long string, which rotates as a rod. So classical solution with just rotating string, energy being proportional to the square root of the spin, and we can expand near that. And in fact, in flat space, it's not that hard to understand that the two expansions are somehow related, though the expansion near different factor. So essentially what we'd like to do is to try to use similar intuition in the case of AdS5S5. So we may try to look at classical string solutions, classical string motions, and then perturb near these different points, and then try to connect them once we include fluctuations. So maybe that way we can map the whole space of states, at least at large lambda. And I'll demonstrate how that works in more detail. So again, I'm referring to the simple fact that in classical space you can just look at small string oscillations and build up spin from oscillations. On the other hand, you can just consider string carrying large spin from the start. And the two obviously is related. So it's interpolation between one loop quantum fluctuation and classical expansion near classical string trajectory. So let me set up some notation and explain basic solutions I'll be discussing. So Poincare and global coordinates, we can use any of two of them, Minkowski signature. So this is Poincare and this is global, and these are related by this redefinition. Remark I will need probably at the very end of my talk is that if we look at string energy in global coordinates, that's how it looks like. It's essentially this cosh t dot, it's density, but we can re-express it in Poincare coordinates. And that's basically what gives the dimension of the corresponding operator in gauge theory. It turns out that for these simple solutions which we'll be discussing, this energy, the global energy in global coordinates, is actually the same as energy in Poincare coordinates. That seems, I don't know very clear the explanation for that fact, but it's actually useful for discussion of non-conformal cases once I get to them. So simple solutions which I'll be discussing are null point-like strings, just like in flat space. Point-like strings means null geodesics, and rotating strings. So point-like string in Poincare coordinates, it's easy to see what's the general solution for null geodesic, and essentially there are two different cases. One is straight line parallel to the boundary, so just very similar to what we have in flat space, x not equal to x1, carrying some momentum parallel to the boundary, or what may be called rotation S5. It's actually a straight line in Z1, Z2 plane, but sitting at Z1 equal 1, so as far as the angle phi is concerned, it carries angular momentum. So in global coordinates, that's exactly just rotation along big circle of S5. sitting at the center of AdS. And that was discussed several times already. So folded string rotating AdS5, again, that was mentioned in the talk, discussed in the talk by Igor Klebanov. So in global coordinates, that's the solution, which was first found by De Vega and Gisquiza, I believe. So here's raw coordinate, which depend on sigma, and the rest of coordinates depend on tau. In point-correct coordinates, it looks very strange. It's a string which carries angular momentum with respect to the boundary, and it moves towards the horizon, rotating, stretching, etc. So the important point is that the energy of this rotating solution at large spin, it goes as square root of spin for small s. S is a parameter of classical solution, essentially these frequencies. And for large spin, it goes as s plus log s. So what I do now is trying to expand near point-like string configurations in AdS5, S5, including quantum corrections. So we can look at classical energy, classical angular momentum, and then compute corrections in alpha prime, which means 1 over square root of lambda. So string theory is defined on a cylinder. So that's the solution. So simple case, which is similar to flat space, is the one which is parallel, geodesic parallel to the boundary. In this case, it's easy to see that one loop correction is just exactly as in flat space. So string, point-like string moving parallel to the boundaries, fluctuations do not see the curvature. But two-loop correction would be very interesting to compute because it's certainly non-trivial, and it will contain dependence on momentum and 1 over square root lambda. So that's related, well, in plane wave sort of framework, well, logic, that would mean that Penrose limit of this case is flat space. So it's not interesting, but beyond plane wave limit, certainly there are corrections to the energy. So geodesic rotating S5, so here the solution I just discussed, all other coordinates AdS5 and S5 are trivial. So that's the energy, that's the angular momentum. So it's important that we fix parameter of classical solution. In this case, it's angular momentum J over square root of lambda, it's fixed. And we look at states which carry this angular momentum in quantum theory. So to one loop approximation, just starting with the sigma model, including fermions, doing straightforward expansion, working out gamma matrix, etc., you end up with the action, which should be familiar from some previous talk, which is the action found by Metsaev in the plane wave background. So essentially, the history was kind of strange in the sense that one doesn't really need to go through plane wave Penrose limit first and then quantizing Green-Schwarz in this background. You can just quantize Green-Schwarz in AdS5, S5 near this classical solution. That's what you get. Essentially, implicitly, that understanding was already in BMN paper, and that was made explicit in paper by Gapsak, Klebanov, and Polikov. And in fact, in the paper with Frolov, which I should have mentioned in the beginning of my talk, which is basically contains many points of this talk, we worked this out in detail. And so the idea is now to go beyond this one loop approximation. We can look at higher orders and try to see what we learned there. The general procedure is, since we expand in near solution, which time is equal to tau, it's just like static gauge. The two-dimensional energy is proportional to the 10-dimensional energy. So E minus J here is expectation value of two-dimensional Hamiltonian. And in the action I just have shown you, we have 4 plus 4 massive bosons and 4 plus 4 massive fermions. I just remind you that these massive terms come from curvature, and this term comes from phi form. And indeed, the divergences cancel, and there is a two-dimensional supersymmetry here, etc. So that's what we get at one loop approximation. We fix nu again is the frequency of rotation. In terms of J, that's the formula which was discussed in several previous talks. So here we observe that miracle that we can re-expand this formula in lambda, or lambda prime, which is lambda over J squared. And the question is, what happens at higher orders? So the action we're dealing with is essentially sig model of that type, but all fields are massive. There are 8 bosons and fermions, massive with nu appearing in the vertices. And before I proceed, So what I'm aiming at, understanding how the higher order terms in this formula, what's their structure. So first let's discuss parameters. We're using just standard string theory expansion. So we have alpha prime of r squared, which is 1 square root of lambda, which is less than 1. Nu is fixed. It's our parameter of our solution, which is nothing but lambda prime in some papers and previous talks. G string should go to 0. So we're just expanding in string theory. So if you just look at these parameters, how they are related, so the square root of lambda is suppressed by 1 over j. So if we take this BMN limit where we fix lambda prime, take j to infinity, G2 is going to 0. We're expanding it. That's what we get. We get one loop approximation in classical string theory, but in principle, we may need to include string corrections. So this is just the, I stress this is just standard expansion reinterpreted. So if we take j to infinity, then we can ignore higher order alpha prime correction. But let's keep them, and the L loop order correction, in fact, turns out to have the following structure. It's power 1 of square root lambda. This function vanishes at large nu. It vanishes for ground state because it's supersymmetric theory. And essentially one sees that indeed y with these near BPS states we don't get randomization. For states with large j we do not get randomization. It's kind of clear from worldsheet theory. But if we relax j infinity condition, certainly the anomalous dimension is corrected. So here is just for illustration how two-loop computation may look like. It wasn't completed, but the leading two-loop correction looks like lambda over j cubed. Lambda over j squared appears from the square root term. So that looks like you may be able to see this in, if this logic works, in the one-loop computation of anomalous dimension beyond the limit which was considered in previous papers. Papers of Gross, Mikhailov, and Royban, and Zanon, and the collaborator. So let's look at now, so I stopped now with this geodetic running around S5. Let's look at rotating string in AdS5. That's the case which we'll discuss in Klebanov's talk. So here, the solution is parameterized by classical parameter S, which is fixed. Spin is large because it's square root of lambda times S. This is the energy for large S, and it contains this log, which was observed in this by Gapsur, Klebanov, and Polyakov. And now we ask, what is the dependence on S in string theory, in this worldsheet theory? So classical string theory, but always in lambda. So this is non-BPS case, and so here certainly we have non-trivial randomization. So we expect maybe there are higher logs, and actually very complicated depends on S at higher loop orders. So the claim is that all, indeed, log S is the term which will be dominating at large S. There's no higher order terms. They all vanish. And we can compute this function order by order in 1 over lambda expansion. In fact, we computed this coefficient explicitly. So essentially, that repeats this analysis of small fluctuations near null geodesic in this case, though here it would be technically somewhat more involved. So I stress that we don't see higher logs on gauge theory, as was emphasized by in the Klebanov's talk. So we must not, if this AdS CFT kind of works in this case, we must not see them on string theory. And indeed, here it follows from relatively simple scaling argument why the log S should be the leading correction. So essentially, working out Green-Schwarz action in AdS5S5 near this rotating string configuration, we get a theory which contains several fields with mixed fields with masses which depend on sigma, because here the radial direction is dependent on sigma, so it's not constant masses. But they're actually approximately constant, as I'll show in next transparency, if we take large spin approximation. So the fermionic part can be also understood by doing some sigma-dependent rotation. We end up with massive fermions. So massive bosons, massive fermions with mass of fermions, also determined by the same function rho prime, which is just some function of sigma. Rho is some hypergeometric function solution of some first-order differential equation. We don't really need to know details of it. So we have some rule here. It's ultraviolet finite theory. It's non-supersymmetric configuration. Supersymmetry is broken here. Two-dimensional supersymmetry is broken here. And also there's no global supersymmetry on that solution. So we do expect correction to the vacuum energy, and we just compute that correction by taking expectation value of corresponding Hamiltonian. And at large S, it boils down to the just computing some finite sum of finite number of terms, bosons and fermions combined together. This sum is finite, and you get you observe that there are no higher logs, and the leading log S correction is this one loop correction with some given coefficient. So higher orders, just similar analysis, but including interactions in the sigma model. And it turns out that the two-dimensional energy always scales as mass squared for large mass. So mass is here, this k, which is proportional to log S. So details are not really terribly important, but it's just scaling argument. You just think what happens on a cylinder in a massive theory with these interactions, and you learn that the two-dimensional energy scales as k squared, where k is log, divided by 1 over k, which is coefficient between proportionality between time and tau. So this is space-time energy, this is two-dimensional energy. So the conclusion is that there are no indeed higher logs, so it looks like it's a nice test of AdS CFT. So there is no higher logs in anomalous dimensional gauge theory side, there are no higher logs in string theory, in classical string theory. So now let's look at more complicated case, and the idea is to test this philosophy that starting with one expansion point, including fluctuations, we can build up, say, spin out of string running around S5. And then can we reproduce the same formula which we got on classical level, just looking at spinning string? So the solution which I want to look at, which carries both J and S, and its energy will be complicated function of J and S, classical energy. And the solution is just like helicopter. It runs along S5 and rotates along the boundary AdS5. So it has spin, J, and energy. And in small spin limit or short string limit, it's the same dependence as in flat space, momentum squared plus spin. So if you expand this formula for J being much larger than spin, so frequency being much larger than this classical parameter related to spin, that's the formula, J plus S plus correction proportional to S. So what's the significance of this formula? So that's the formula which we get for classical solution containing both J and S. Compare this to formula for this famous square root formula, which is obtained by including fluctuations near solution with J only. So if you take states on leading radial trajectory, you get spin out of this n factor. And the two formulas agree. And this is not completely trivial. Well, this lambda term is indeed just like in flat space, expected one. But one comes here and here from the curvature of AdS. So leading linear term in S indeed is, as one could expect, is related to curvature of AdS. So in a sense, that checks this philosophy that indeed we can relate different expansion points. It would be very nice to study different cases, let's say oscillations, oscillating string, etc., which are stable classical solutions, and try to see these interpolations. So essentially, including fluctuations, we probe some directions which move us towards another expansion point. So one can think also of operators related to these states for small s, for large j, and it would be interesting to try to check this formula at the gauge theory side as well. So that should be one loop correction, how it depends on spin. So it's an operator which contains both large j and some spin, some number of derivatives. Well, there are various generalizations, maybe. How much time?
No, it's under 5 minutes.
Under 5. Okay. Maybe I mentioned that in the other limit, there are several limits here, several limits of parameters. For example, there is a limit when there is no log s term. So j may suppress this log s term, which we get for large spin. So various generalizations would be interesting to study. I guess I will not really comment on them. Let's try to think what we may get in non-conformal cases. After all, we're interested in non-supersymmetric non-conformal cases. Can we use similar philosophies, say, by taking some D3 brane and conifold geometry and trying to compute corrections to anomalous dimensions near AdS points? So just perturbing a little bit away from conformal point. And essentially, that's what is done in the Young-Mills theory, which has ultraviolet fixed point. So we look at anomalous dimensions. They depend on coupling. Coupling may run, but we can isolate running coupling from corrections. So we can try to see how this happens here. So suppose we take this metric and look again for classical solutions, which say rotating string along big circle of S5, and expanding this geometry in the region which is approximately AdS. So there is a parameter in this case, which is m squared over n, which is a number of fractional differential branes squared divided of number of ordinary free branes. So going through analysis how the solution changes, and here we use point correct coordinates, that's why I was referring to them earlier, one can compute correction to the energy. It turns out that the leading correction vanishes. So that means there is no correction to the dimension of the corresponding operator in this SUN m plus m theory to leading order in m squared over n. And that is interesting because there may be a way to understand this from gauge theory, why this correction vanishes. Similar observation was done in our earlier paper about the simplest chiral operator, which is related to running of couplings. It gets correction only at higher order in Mn also, which was a little bit surprising. So one can look at similar story for spin, and here it looks like indeed there is a correction which is non-vanishing and leading order correction, which depends on tau. So what that means, running with tau, energy is not conserved here, of course. Energy is related to anomalous dimension, so running in time should be related to running of gauge couplings. So let me just summarize. So what I discussed is point-like string in S5, running in S5. Here we can fix nu, expanding square root of lambda, and it's useful to think how these higher order terms are actually, what are the constants in them. In particular, to loop computations should certainly be completed, though the technology exists. It's just not so simple computation. In fact, that is related also to what was mentioned in John Swartz's talk. So for the string here, I argued there is no higher logs. We can compute these coefficients. Again, it's interesting to see whether we can interpolate eventually to gauge theory results. And it's certainly important to study non-conformal cases. And here, finally, conclusions is that I would like to stress that Green-Schwarz action, I'm very happy to give this talk here because one of these letters is an organizer. So Green-Schwarz action is a practical tool for exploring gauge string duality, at least at large lambda expansion. So especially in semiclassical expansion. It looks like lots of things can be done still here. So we certainly have seen during the last few months interesting progress in understanding part of string spectrum at large lambda in this JS spectrum sector, and for large J this goes probably beyond just leading order in 1 over lambda. And extension to non-conformal cases, it's interesting to stress the point that at least log S should be generic. We are told that this should be the case in non-supersymmetric cases, non-conformal cases certainly. So we should be able to see that also by studying through similar logic in these cases, other cases. Thank you.